Good morning, everyone. I am Narmatha, Assistant Professor, Department of Cybersecurity, working in Dr. S.N.S. Rajalakshmi College of Arts and Science. In today's lecture, we are going to discuss about deadlock avoidance. So, in this lecture, we'll see about what is deadlock avoidance, safe state, unsafe state, and banker's algorithm. Deadlock avoidance requires that the system has some additional prior information available. Simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. Resource allocation state is defined by the number of available and allocated resources and the maximum demands of the process. Safe state. When a process requests an available resource, system must decide if immediate allocation leaves the system in a safe state. System is in safe state if there exists a sequence P1 to Pn of all the processes in the system such that for each Pi, the resource that Pi can still request can be satisfied by currently available resources plus resources held by all the process J with J less than 1 condition. Basic facts that includes if Pi resource needs are not immediately available, then Pi can wait until all Pj have finished. When Pj is finished, Pi can obtain needed resources, execute, return allocated resources, and terminate. When Pi terminates, Pi plus 1 can obtain its needed resources and so on. If a system is in safe state, no deadlock. If a system is in unsafe state, possibility of deadlock. Avoidance means ensures that the system will never enter an unsafe state. Safe, unsafe, deadlock state. So that is represented here. Safe state means in that it doesn't have a deadlock. In unsafe state, it may occur a deadlock situation. So that picture is represented. Safe, unsafe, deadlock state. A safe state is not a deadlock state. Conversely, a deadlock state is an unsafe state. Not all unsafe states are deadlocks. An unsafe state may lead to a deadlock. As long as the state is safe, the operating system can avoid unsafe states. For example, we consider a system with 12 magnetic tape drives and 3 processes P0, P1, P2. Process P0 requires 10 tape drives. Process P1 may need as many as 4. Process P2 may require 9 tape drives. Suppose that at time 2, process P0 is holding 5, P1 is holding 2, P2 is holding 2. So that is represented in the tablet form. At time T0, the system is in a safe state. The sequence P1, P0, P2 satisfy the safety condition. A system can go from a safe state to an unsafe state if the resources are unavailable. Process P0 must wait. Similarly, process P2 may request an additional 6 tape drives and have to wait, resulting in a deadlock. So the avoidance algorithm is used to ensure that the system will always remain in a safe state. Initially, the system is in a safe state. Whenever a process requests a resource that is currently available, the system must decide whether the resource can be allocated immediately or whether the process must wait. The request is granted only if the allocation leaves the system in a safe state. Avoidance algorithm. Single instance of a resource type, use a resource allocation graph. Multiple instances of a resource type, use the Banker's algorithm. Resource allocation scheme. So by using the resource allocation scheme, all the resources are allocated by using the graph structure. So see here graph representation of process P1 and P2 with allocation of resources R1 R2 is represented. So by using this resource allocation graph algorithm, we can decide that it doesn't have a cycle form. So from this lecture, you can understand about how we are avoiding the deadlock. So what are all the algorithms we are using to avoid the deadlocks as given. Thank you.